And so you need the calcium side of it to degrade the cyclic AMP after the made. So the calcium side is taking over. For everything on the calcium side. That's the point. Okay, why do you need a cyclin? All right, so here's why, okay? So we went through last Friday this whole process by which different labs working on different systems to all figure out how the cell cycle works. So Hartwell does genetics in yeast, finds over 100 genes that are required for the cell cycle, and has a very productive career figuring all of those out. So he had like 100 different CDC genes, figured out what all of them did, okay? Meanwhile, Tim Hunt's lab largely leads a biochemical approach using marine organisms and amphibians to try and find proteins that their appearance and disappearance correlates with this magical activity which is called maturation or mitosis promoting factor. So remember at the time, they didn't know what the biochemical activity of MPF was. They just knew it was an activity that was capable of driving cells from G2 to M. But they didn't know what it did, okay? They didn't know how many subunits it had. They didn't know if it was a protein kinase at the time. So after about the sum of 10 to 15 years worth of work, it came to the realization that MPF is a specific type of a cyclin CDK complex, okay? And the idea is that the catalytic subunit over here is inactive by itself. So, and we refer to that as the CDK, okay? So the catalytic subunit There's 4 or 5 of them in eukaryotic cells, but don't get hung up about the numbers. The key thing to understand is the catalytic subunits do not undergo periodic synthesis and destruction nearly to the extent that the cyclin subunits do, okay? And the key thing is understanding that the catalytic subunit all by itself can't phosphorylate substrate proteins. It requires an association with a cyclin subunit, okay? So early in the cell cycle, when a cell is leaving a G0 arrest and going into G1 in an S phase, it's going to be cyclins D and E that associate with an inactive CDK. And then as we move past those phases of the cell cycle, the Ds and Es are degraded and they're replaced by the mitotic cyclins A and B. So then they interact with the CDKs. And in essence, what you're changing are going to be differences in proteins that are phosphorylated at different times in the cell cycle. And you're going to be phosphorylating them in different places. Okay? So the basic catalytic subunit then of a CDK is inactive because it has this little alpha helix up here that's juxtaposed to a region called the T loop. And the T loop blocks the substrate binding site. Okay, it's locked in place. ATP is bound, so that's not a problem. But what it does, it prevents the proteins that are going to be phosphorylated by a cyclin CDK from binding and having the hydroxyl group on either their serines or threonines close enough to that terminal phosphate to be phosphorylated. That's why we need the cyclin subunit. Okay? So the cyclin subunit, it's much smaller. And when it binds to the inactive CDK, what it does is you can see we get a conformational change in the alpha-1 helix and also predominantly in this T loop. And you can see really dramatically, it actually gets pried back. Okay? So the cyclin subunit literally pulls that T loop away, and in doing so, that opens the substrate binding site and will allow it to be phosphorylated by ATP. All right? Now, that's a start. Okay? That's a start. And what I mean by that is that if you just take a cyclin and hook it up with a CDK, it will have kinase activity, but it's not very robust. So it's a low activity kinase. And what you notice up there is that one of the important amino acids on the CDK subunit is a conserved threonine. And it's either a threonine 160 or in some other organisms, it's a position 161. Okay? So you notice that you see as we go through these figures, you're looking here and you go, wow, it's threonine 160. But then a couple slides from now, you go, wait, it became threonine 161. It just depends on which position in a CDK that threonine is actually found. But they do the same thing, and they have the same function. So the important thing is that threonine has to be phosphorylated in order to ramp up a cyclin CDK to make it very, very high activity. And we're going to get into the mechanism by how that happens this morning. But here's why you want to do it. You have to think of these kinases that are driving the cell through the cell cycle. You don't want them to be gradually, like having all this. This is not a situation where you want a low activity kinase gradually phosphorylating its substrates over a very long period of time. And the reason is that you want these cell cycle transitions to be abrupt. Okay? You don't want the cell to gradually enter mitosis. Okay? You want the release of a very active pool of MPF or a cyclin CDK. You want a very active pool of that kinase to be released and to start phosphorylating all of its substrates very quickly at the same time. And the reason is that especially when you're looking at going into mitosis, when the cell goes into mitosis, one of the substrates is going to be breaking down the nuclear membrane, causing it to depolymerize, causing your chromosomes to condense. Because of that, when the cell goes into mitosis, it pretty much shuts down every other activity going on in the nucleus. You shut down transcription. You shut down DNA replication. So in order for that to happen, you want it to occur all at once. You don't want to start gradually depolymerizing your nuclear membrane. You don't want to start gradually condensing your chromosomes. You want those to happen at once. And so you're going to see that is why this phosphorylation of threonine 160 or 161 is going to become a mechanism to allow that to happen. So what it's going to do is imagine what's going to occur, particularly during G2 of the cell cycle. The cell is going to be accumulating a very large, inactive, completely inactive pool of a cyclin CDK. And that's because there's going to be some other phosphorylation events occurring on the CDK. And then, once we hit a point where certain requirements have been met, boom, we can now activate this kinase, have a very, very large pool of it to immediately go in, phosphorylate substrates, and the cell makes an immediate and abrupt transition into mitosis. Okay? All right. So what about the cyclins themselves? What accounts for their periodicity? Well, you can take a look at this, and this is GFP tagged cyclin B. It's pretty obvious. Just watch what it does. So one of the things you notice up here, this cell here is going through mitosis. And what you can see is, look at this cell here first. As it's going into late G2, see how the fluorescence intensity increases? That's what's showing you that the cyclin B level is accumulating during G2. Okay? And you can also tell that during this time, notice that the fluorescence is excluded from the nucleus. Now the nuclear membrane is keeping that from happening. So the cyclin B is accumulating in the cytoplasm. What you notice here now, here's a cell that's undergoing mitosis. Look where the fluorescence goes. Can you guys see the fluorescence go into the nucleus, and it's associated with the mitotic spindle? Because cyclin B CDK is going to have a function in the mitotic spindle as the cell goes through mitosis. But look how quickly the fluorescence goes away. It's gone there. There you go. So that actually shows cyclin coming up, and then it drops away very quickly. It gets degraded. So it was starting with an experiment like this that Hunt's lab was able to determine, okay, what accounts for cyclin's ability to undergo this rapid degradation? And so this experiment here is showing you what you would find if you took GFP and hooked it up to all of cyclin B. Well, if you want to find the sequences in cyclin B that are responsible for its degradation, you just start taking smaller and smaller regions from cyclin D or B, smaller amino acid sequences, and putting them onto GFP. And in essence, what you're trying to do is you're making a chimeric protein, where what you're trying to identify what sequences are found in cyclin A or cyclin B, that if I put them into GFP, GFP will behave like an intact cyclin. Okay? So that's the basis for the work that he did. And this is how Hunt's lab delineated within the cyclins A and B, the mitotic cyclins, a conserved amino acid sequence that they called the destruction box. And the reason they called it a destruction box is that these were the amino acid sequences that were responsible for cyclin being degraded as cells went into mitosis. Okay? The destruction box, as you can see, so here's cyclin A, cyclin B1, B2, two different isoforms of cyclin B that are found in Xenopus. And what you find is the destruction box contains a series of very, very conserved amino acids. If you go in and alter any of those conserved bolded amino acids, what you wind up with is non-degradable cyclin. You're not able to drop its level. And you're going to see that when we move into mitosis on Friday, that's going to have profound effects on the ability of the cell, not so much to go into mitosis, but to be able to get out of it. Okay? Turns out there's one other amino acid that you need in order for cyclins to be degraded, in addition to the destruction box. And that is, at a fixed distance away from it, you will always find a conserved lysine. Change that lysine to any other amino acid, and you keep the destruction box intact, and that also generates non-degradable cyclin. Okay? So what are these sequences doing? Well, you've already seen this process before. Remember that unfolded proteins that are eradicated out of the ER, they go into the cytoplasm. They're recognized by a series of enzymes called ubiquitin ligases. And they ubiquitinate the protein, and that causes it to be targeted to the proteasome for degradation. Okay? The ubiquitin itself is added onto the lysine. The recognition site for the ubiquitin ligases that are going to add it to the lysine bind to the destruction box. So destruction boxes are nothing more than high affinity binding sites for ubiquitin ligases that can recognize these proteins. Now they're properly folded, so understand this isn't associated with protein misfolding. Those cyclins are normal, they are folded properly. What they have, though, is a very high affinity binding site for ubiquitination. Okay? And that's what causes their degradation. Now, it turns out that the ubiquitin ligase activity itself here is required for cells to go into anaphase. So what we're going to do is we're going to start referring to this ubiquitin ligase activity by a different name. And we're going to refer to it as the anaphase promoting complex, or APC. Think of it this way. You need a cyclin CDK to go into mitosis. And that's what MPF does. MPF is going to be responsible for taking you all the way from G2 to metaphase. Chromosomes are going to be lined up on the equator. You're poised, you're locked, you're loaded, you're ready to divide. You need the anaphase promoting complex to execute the next part of the cell cycle. And that is to get rid of the cyclin. That inactivates MPF, so now the kinase goes from active to inactive, and the cell can move into anaphase now. Okay? So we're going to see mitosis as a two-part process. It's got an MPF part, and then it has an APC part. Okay? Now here's where it gets even more interwoven, or more interconnected. And that is, cyclins are suicidal. Not only do they have the information it takes to ensure their own destruction, they activate the APC. So the mitotic cyclin CDKs, one of the proteins that they phosphorylate is a component of the anaphase promoting complex. So they are literally pointing the gun at their own head, but they're also putting the bullet in the chamber and cocking it and shooting it. Literally. I know it sounds extreme, but you're very, very rarely ever going to find a protein that enables its own self-destruction as much as a cyclin. Okay? So it's a beautiful system to illustrate how you can make sure we can go into a step in the cell cycle, but also make sure that we get out of it. So here's how they're going to commit suicide. Okay? Now this is simplified, and I've made it even simpler just out of the interest of time. So everything up here with the black box over it, just ignore that. It's really not germane to mitosis. Okay? Let's start down here. We've got a cell that just came out of mitosis. Okay? We're done. There's no cyclin subunit. So for a cell that's going to go through G1 and S, we're going to have cyclin Ds and Es come and go. Don't worry about those. Those are gone. What we're looking at here is a cell that has completed DNA replication. It's now going into G2 phase. Okay? During that part of the cell cycle, then, we've got an inactive CDK. Can't do anything. But what we're going to be doing is we're accumulating cyclin A CDK. As it accumulates, it's going to bind to the CDK, which is inactive. Now, we're going to have a separate mechanism to keep this complex from being active until a certain point. But once it becomes active, that cyclin B or cyclin A CDK is going to phosphorylate a subunit on the anaphase promoting complex. Until that happens, the APC is inactive. Okay? So one of the substrates for MPF, and you're going to see when we get to mitosis what all these different substrates are. But one of the substrates right here is a subunit of the anaphase promoting complex. And that is necessary to turn it on. Okay? But this is going to be the executioner that is now going to polyubiquitinate the cyclin subunit. So the cyclin CDK turns on the APC. The APC immediately turns around and says, thank you, and it ubiquitinates the cyclin subunit, and bang, it's gone. There goes your MPF activity. The kinase is now shut off because the cyclin subunit is degraded. Now, the CDK hangs around, but it can't do anything without the cyclin. Now, make a note. Can you see what happens if we make it impossible for the cyclin subunit to be degraded? That's basically going to keep MPF activity high when it should be coming down. And you're going to see that's going to perturb mitosis in a lot of different ways. But the key thing here is that once the APC is active, it ubiquitinates cyclin, it's gone, MPF activity shuts off, and the cell now goes into anaphase. Make a note. This is not the only protein that the anaphase promoting complex is ubiquitinating and degrading. Cyclin is one of them. But there's another important protein that's involved in holding your chromosomes together on the mitotic spindle. And this protein is called securin. Secures your chromosomes together. It has to be ubiquitinated and degraded to allow the sister chromatids to go their own way during anaphase. Okay? So the important thing is there are multiple substrates for MPF. There are multiple substrates for the anaphase promoting complex. But right here you guys can see cyclin is responsible for activating the anaphase promoting complex. Okay. So here's a throwback to a situation we just went through. Remember when you guys looked at epinephrine-dependent signaling in liver cells, all that. Remember that when pKa gets active, it's phosphorylating proteins. We shut off the phosphatase during that process because pKa phosphorylates an inhibitor of the phosphatase to turn it off. You see this every time. Anytime you activate a kinase, you turn off the phosphatase that's going to reverse that. You want to put the phosphates on, you want to keep them on. Here's where you can see the same thing with MPF. Okay? And again, this graph very nicely, this comes from a little review article from Hunt's lab a few years ago. And here's what it shows, is that you notice when a cyclin CDK is inactive, that the phosphatase, in this case it's called PP2A, protein phosphatase 2A, it's always active. Phosphatases are generally constitutively active. They're just going around taking off phosphates as they show up. But look what happens. Now when we go into mitosis here, and we start activating a cyclin CDK, consider this MPF activity. As MPF activity starts to ramp up, the phosphatase gets turned off very rapidly. And here's why. This is a Western blot showing you the inhibitor of the PP2A phosphatase. Okay? It's just like IP, that same protein that inhibits the protein phosphatase that DKA takes out. So here's the protein. And notice you see a difference here on the Western blot. As soon as we get to where MPF comes on and the phosphatase is shut off, notice that we see this stepwise increase in the size of the protein. That is due to its phosphorylation. Many times phosphorylated proteins on SDS gels migrate slower than their non-phosphorylated cognates. Just like when you glycosylate a protein, it adds mass and it retards its migration. Phosphorylation does the same thing. So anytime you're running a protein and you're looking at it on a Western blot, you notice a difference in size of the same protein under different situations. Two questions you ask. Is it undergoing glycosylation or is it undergoing phosphorylation? Okay? Because phosphorylation reduces its migration. So here's what happens, and look how rapidly that takes place. So this inhibitor is phosphorylated very rapidly as MPF activity comes up. But now, right here, this is when the cyclin subunit would be ubiquitinated and degraded. So look how rapidly our kinase comes down. And look how rapidly, when the kinase comes down, remember, we always have a little pool of free phosphatase that's never inhibited. This shows you how quickly that works. Because very, very rapidly, as soon as we shut the kinase off, the little free pool of PP2A immediately dephosphorylates the inhibitor, and that's what frees up a big pool of the phosphatase. We go through another cell cycle, and our inhibitor remains dephosphorylated, and then boom, we go into the next round of mitosis. The protein gets rephosphorylated as MPF activity comes up, and then it goes down. So remember, guys, we always have this reciprocal relationship, or inverse relationship. Kinase goes on, inhibitor of the phosphatase goes on by being phosphorylated by the kinase. You get out of whatever the kinase did by blocking the phosphorylation of the inhibitor, and now the free phosphatase goes back to work. So now you guys have already seen two substrates for MPF. The first substrate for MPF is the anaphase promoting complex. It turns it on. The second substrate for MPF is the protein phosphatase inhibitor to shut the phosphatase off. And again, the reason we're doing this is to make sure that all these proteins that get phosphorylated by MPF remain phosphorylated for the duration that the kinase is active. Okay? All right. This was really cool. This is all it takes, by the way, to win a Nobel Prize. Okay? This came out of Hunt's lecture for the Nobel, his acceptance speech for the Nobel Prize. That's all you have to do, is to explain it. We go from interphase to mitosis by making a cyclin. We go from mitosis back to interphase by basically degrading cyclin. And cyclin specifies its own destruction. Congratulations, go to the King of Sweden, pick up your prize, go home. Life is good. And then you go, gee, what happened? Well, here's what happened. Okay? Gets a lot more complicated. Okay? So if we take a look at a cyclin CDK complex, these kinases are regulated by a lot of extrinsic factors that are coming in. We're only going to look at two of them. And we're only going to be looking at the G2 to M cyclin CDKs. And here's the two things that we look at. One, we don't want a cell to enter mitosis until that little structure called the centrosome. Remember that? What's another name for the centrosome? For the MTOC, sweet. It's the MTOC. It's the microtubule organizing center. It's got two centrioles. The MTOC has to duplicate to make a mitotic spindle. We don't want to go into mitosis with only one MTOC. We want to make sure we got two. So we don't want to turn this guy on and activate it until the centrosomes have duplicated. So that's pause, let's wait for that to happen. The other reason we have to pause is what has to happen during G2. The cell has to double in size. Okay, those are the two things we're looking at here. We do not want to turn this kinase on, even though there's a cyclin subunit bound to the CDK. We do not want that kinase active until the centrosomes have duplicated and the cell is doubled in size. So this brings us to the last part of the cell cycle, because we're looking at the regulation now. Okay? If we take a look at the top, this is what we're doing right now. We're basically looking at how two kinases and a phosphatase work together, and they're going to link the activation of MPF with cell growth and centrosome duplication. It's actually tied in with DNA replication too, because the centrosomes duplicate during S phase. They duplicate at the same time your DNA does. So that's what we're looking at here. File that away down here, because in a couple of weeks we're coming back. These are ways that we can also inhibit cyclin CDKs, and these are going to be tumor suppressors. These are going to be mechanisms by which we can take any cyclin CDK at any part of the cell cycle and shut it down because we've had damage to DNA, mutations. These are tumor suppressors because they prevent cells from proliferating after the DNA has been damaged. The reason we have these tumor suppressors is to stop the propagation of mutations that have generated oncogenes. And what you guys are going to see is a failure of these tumor suppressors that are the initiating event to allow a normal cell to become cancerous. Okay? All right. So now we're switching to the last yeast of the section, and this is Paul Nurse's lab working in Scotland on the fission yeast, Schizosaccharomyces pombe. You can see it doesn't divide by budding, it divides by fission, which is why it got the name schizo. Here's something to bear in mind. This is a unicellular yeast. Mechanistically, and at the molecular level, these cells regulate cell division much more closely to our cells than they do Saccharomyces cerevisiae. So Schizosaccharomyces pombe has a much more sophisticated cell cycle than Saccharomyces cerevisiae. This is actually a closer organism to look at for cell cycle dynamics than using Saccharomyces cerevisiae. And the reason is, Schizosaccharomyces pombe, what we can look at here is that the cells have to elongate, you see it right there, before they undergo mitosis. Okay? So this is the starting point for what Nurse's lab did. Okay? So Nurse is going to go into Schizosaccharomyces pombe, and he's going to make temperature-sensitive mutants, just like Hartwell did. And what's going to happen is that when you shift the cells to the non-permissive temperature, what he's looking for are mutants that don't follow cell size. So we found two categories of mutants in Schizosaccharomyces pombe, that if you shifted the cells to the non-permissive temperature, you saw one of two outcomes. These guys over here here's what they normally look at. So that's about the size that the cells normally get before they divide. So that's normal. You can have cells over here where the duration of G2 was elongated. G2 is longer than it should be. To think about it, it means the cells are getting bigger than they normally would before they divide. Okay? So the ability to go into mitosis is slowed down. The students in the lab noted, they said, well, gee, the cell cycle in these cells is being strung out. So they described this particular mutation as string. It's stringing out the cell cycle. Okay? But they also found in the same lab, they found another mutant that had the opposite effect. And this is my favorite protein in the unit. This little guy, WEE1. And the cool thing about WEE1 is, when it doesn't work at the non-permissive temperature, you divide too soon. So you can see here, the cells don't have an opportunity to double in size. And that is, they're going to be doubling quicker. They're going to be dividing before they're able to do that. So remember, these are loss of function mutations. So here's something to bear in mind. The WEE phenotype comes about because the WEE gene is not working. Okay? The string phenotype comes about because the string gene is not working. The gene is named after the mutant phenotype, just like Drosophila. So what it means is, the normal function of WEE over here, the normal function of the WEE gene is to keep you from doing that. The normal function of WEE is to make sure you divide normally. The normal function of string is to make you not take so long to divide. So what it means is the following. WEE is a negative regulator of cell division. String is an activator. And what you see is, it's actually remarkably simple, what these two guys are doing. They're targeting the CDK. And they're targeting the same amino acids on the CDK. And here's what you guys are going to see. WEE1 is a dual specificity kinase. Here's where you guys get tyrosine phosphorylation at last. It's a dual specificity. And what WEE1 does is it keeps MPF from being active too soon by phosphorylating two amino acids that are adjacent to each other. A threonine at position 14 and a tyrosine at position 15. That shuts MPF off. CDC25 is string. CDC25 is a dual specificity phosphatase. So CDC25 reverses the effects of WEE1. So we've got a kinase and a phosphatase. This is to stop the cell cycle. This is to allow it to go into mitosis. Okay? So here's how we're going to put these two activities together. Okay? We're just going to regulate MPF activity. So here's what we don't want to happen up here. You don't want to enter mitosis too soon. That's a WEE phenotype. You don't want to enter mitosis too late. That's a string phenotype. So here are the three players that are going to come into play that are going to link the activation of MPF with all of these events that have to take place before the cell can enter mitosis. Okay? So here's what's going to happen. As we go through G2, we're accumulating a mitotic cyclin. Cyclin A, cyclin B. They come together. Now remember, that's going to give us a trickle of MPF activity unless we stop it. That's what WEE1 is going to do here. So what happens is, as we put these two subunits together, WEE1 is going to phosphorylate. There's our two amino acids. Threonine 14, tyrosine 15. They're right next to each other. The same kinase hits them both at the same time. This completely shuts off MPF activity. So now you guys can see, we're building up a pool of inactive kinase. Every time we make a cyclin subunit, it binds to the CDK, it's phosphorylated by WEE1, and it is shut off. And we want to keep it off until certain things have happened. We want to make sure the centrosomes get duplicated, and we want to make sure the cell doubles in size. Okay? So here's what we need to do next. We need to reverse this phosphorylation in order to remove the inhibition. Well, we don't want to reverse that until something has happened. So what we want to do is we want to make sure we're not going to remove these phosphates until the cell has doubled in size. We need something that can measure doubling of size. So you look around the cell and you go, what does a cell have when it's twice as big, that you have twice as many of, than it had before? Ribosomes. So we need a protein that's a ribosome counter. And that is the job of the serine threonine kinase, CAC, for CDC activating kinase. CAC is a ribosome counter. Nobody clearly knows how it's counting. We don't know if it's got a calculator, an abacus, whatever. But CAC is measuring ribosomes. 1, 2, 3, whatever. And as soon as the ribosome count doubles, CAC goes, well, I must have doubled in size. Therefore, I'm going to phosphorylate threonine. Again, this could either be threonine 160 or 161. Just depends on what critter you are. So now threonine 161 is phosphorylated. Cool with that. Now all we have to do to turn it on and have this really very, very robust kinase is to dephosphorylate threonine 14 and tyrosine 15. Here's where CDC25 comes in. CDC25, meantime, what it's waiting to be activated by are when the centrosomes duplicate. So CDC25 is activated when DNA replication is complete. That means there's no single-stranded DNA sitting around, and it's activated by centrosome duplication. So when you have two centrosomes, that activates CDC25. So now CDC25 is active because the centrosomes have duplicated, the cells doubled in size because CAC did its thing, and now what happens is CDC25 dephosphorylates those two amino acids. Boom. Now you've got this big pool of high-activity MPF, and you immediately go into mitosis. You don't trickle your way into mitosis. Okay? All right, let's throw some mutants in here now. If you had a double mutant, if you had a WEE1 CDC, I know, I sound like Claire. Okay. If you have a WEE1 CDC25 double mutant, what's your phenotype? So what's the phenotype of a WEE1 CDC25 double mutant? Do you look like your WEE, or do you look like CDC25, or do you look like your wild type? What you think? Yeah.
Would you be small because you would enter too early first?
Okay, don't say small, say we. Sounds cooler. Okay, do you guys agree that you would have a we phenotype? Think about it. The purpose of CDC25 is to reverse WEE1. If WEE1 is not there, do you need CDC25? It doesn't matter if it's there or not. If WEE1 is not there, CDC25 becomes irrelevant. Okay? What would happen? What's another way we could make a WEE phenotype? By altering amino acids on the CDK. We want to make a WEE mutant in a cell that has WEE1 activity. Which amino acids on the CDK do you change, and what are you going to change them to? Which amino acids are recognized by WEE1? Those two. So what would you change them to? Yeah. Not arginine. We want to keep them from being phosphorylated by WEE1. So who would you change the threonine to? Alanine. Who would you change the tyrosine to? Phenylalanine. F. Here's the first time, guys, where you get to play with tyrosine phosphorylation. So remember, alanine, use that as a substitute for serine or threonine. But if you want to take out the phosphorylation site for a tyrosine, change it to phenylalanine. You're keeping an aromatic ring there, same size, same structure as tyrosine, but you take out the phosphorylation site. So if you guys see that if you make a CDK that cannot be phosphorylated by WEE1, that's pretty much the same thing as not having WEE1. Now here's an interesting question. What would happen if you change both of those amino acids to glutamic acid? Change them both to E's. Can you undo those? Nope. So what's going to happen to your cell cycle time? You're going to have a really long G2. Probably so long you're never going to get out of it. Okay? So you can see that if you prevent those phosphorylation events from happening, you get the opposite effect. Okay? So the point is here, guys, we're not reinventing the wheel. Use the same sorts of phosphosite retroevolution on these three amino acids. And what you guys can see is, now what we can do is change the duration of G2. Okay? So the question is, why do we do this? So why do we make the cell cycle a wee bit more complicated than you might think it has to be? Here's why. Okay? If we're looking at cyclin levels, here's the increase in cyclin level. Okay? What we want to do is if we had no other regulation, and if all it took to activate MPF was to have enough cyclin to bind to enough CDK to make it active, we would reach a threshold level of MPF activity right about here. If MPF activity only depended on the amount of cyclin protein, the cells would divide all the way back here. But what we're doing by keeping MPF activity separate from cyclin level is that now what it means is we're not going to reach that level of MPF activity until we're done with G2. That means we've done two things. Instead of getting the cell to enter mitosis back here prematurely in S phase or G2, now what happens is the cell has doubled in size. Because WEE1 is going to be keeping MPF from being active here throughout this duration of time. So CDC25 is going to be activated as soon as S phase is over. So the phosphatase is active very, very early. But remember, it cannot dephosphorylate the CDK until MPF, until CAC has phosphorylated threonine 160. That doesn't occur until you've doubled in size. So even though CDC25 is hanging around after S phase, it can't work to dephosphorylate threonine 14, tyrosine 15 until CAC has been activated and we've doubled in size. So in essence, what we're doing, this is why we're pushing MPF to be active over here on the right until after we've completed G2. Now, just to finish up. Would you ever want to go through and screw up WEE1 in a cell? And the answer is yes. It could be a cancer target. And the reason that WEE1 could be a cancer target is because, remember, the job of WEE1 is to stop the cell from entering mitosis too early. It's to keep the cell from entering mitosis prematurely. If you put in an inhibitor of WEE1, we inhibit that phosphatase, that kinase. What you're going to get are cells that are now going to start activating MPF, and they're going to go into mitosis before they finish duplicating their chromosomes, before they've duplicated their centrosomes, and before they've doubled in size. So it turns out that WEE1 is actually becoming a hot chemotherapeutic target. Because in essence, what you can do is, paradoxically, you can kill a cancer cell by forcing it to divide prematurely. Okay? So we'll come back and take a look at that when we get to the cancer section. Okay, my final parting words is make sure to get out and vote tomorrow. Okay? Doesn't matter which candidate you want to vote for, but get out and vote. Don't cop out and say, I'm not going to vote for anybody, because you're letting somebody else make that decision for you. Okay? Hopefully we'll be able to come back on Wednesday.